And here we go. So we have this question where we have 1 gram of some acid, HA. Do you remember that HA is a generic representation of a monoprotic acid? It has 1 hydrogen that it can donate. So that is a monoprotic acid, and we dissolve it in water. And our objective is to find out what is the molar mass. We know the mass, and remember what molar mass is. Molar mass is the mass of the acid, and we know that it's 1 gram divided by the number of moles of the substance. Well, that we don't know, but we can determine the number of moles that are in that 1 gram by doing a titration experiment. So we take our 1 gram, we dissolve it in water, we add an acid-base indicator that'll turn color when we've completely neutralized it, and then we're going to add this titrant, 0.25 molar NaOH, a drop at a time until we see the color change take place, and then we know that we have reached the endpoint. And the endpoint, or the equivalence point, is where we've added exactly the number of hydroxide ions required to completely neutralize the number of acid molecules we have in the system. And it turns out when we did that, after adding 19.6 milliliters of this titrant from this burette, it changed color. So that's the number of mils of the NaOH that were required to neutralize the acid. And now we're going to do the stoichiometric calculations in order to find the number of moles of that acid that are in that 1 grams. So stoichiometry, step 1, write out the balanced chemical equation. 1 mole of monoprotic acid will react with 1 mole of NaOH, that is 1 mole of hydroxide ion. Remember that NaOH in solution will dissociate 100% into its constituent ions. And what is special about the hydroxide ion? It's the strongest base that can exist in a stable form in water. So it desperately wants a hydrogen ion to combine with. So it's going to find the hydrogen ion that's attached to that acid, grab it and turn it into water. And so this is our balanced chemical equation for what's happening in that little vessel, that flask, as we add the titrant. Step 2. Now we need to convert whatever information we have been given into numbers of moles. There's only one thing here that we can convert into moles, and that is how much NaOH we have. And we're going to use molarity times volume is equal to number of moles. And so what is our molarity of our NaOH? It's 0.25 moles of NaOH per liter. And what was the volume of the NaOH? 19.6 mils. But since molarity is in moles per liter, we're going to have to use liters as our volume term for that. And that is 0.196 liters. And the liters will cancel, and that will give us our number of moles. And the number of moles is 4.9. Shucks. 4.9 is, this board is starting to waggle again. 4.9 times 10 to the negative 3 moles. Okay, and that's moles of NaOH. So that's step 2. Step 3 is, what's the limiting reagent? Do we have to worry about a limiting reactant in titration experiments? The answer to that is no, because the whole idea of a titration experiment is to add exactly the number of moles of one reactant to completely react with the number of moles of the other. So we added exactly the number of moles of NaOH to completely consume the number of moles of HA. So in a sense, they're both limiting reactants, both our NaOH and HA. But we just omit step 3. It's just not applicable to a titration experiment. So now we're to step 4. In step 4, we're going to take our 4.9 times 10 to the negative 3 moles of HA, no, excuse me, NaOH. That's what we found in step 2 of NaOH. And now we use our balanced equation to convert that into the number of moles of the thing we're interested in. And what we're interested in is the number of moles of acid. And our chemical equation shows us that for every mole of NaOH that was added, we consume 1 mole of the acid. So there's 1 mole of HA for every 1 mole of NaOH. And the moles of NaOH cancel, and that means that we have 4.9 times 10 to the negative 3 moles of HA. Okay. And now we're ready to solve the problem. What was the question? What is the molar weight of this monoprotic acid? And as we show up there, the molar weight of HA is 1 gram is the mass. Molar mass is grams per mole. And we just determined that in that 1 gram, we have 4.9 times 10 to the negative 3 moles of the acid. So divided by 4.9 times 10 to the negative 3 moles, and you do the calculation and get a value of 204 grams per mole. And that is what we were looking for. Right? It's like we got a shiny spot on that's the room light. It's, let me. Is that better? Can you read it okay?
Yes.
Okay. All right. Any questions on this problem? There'll definitely be one of these on the test. I mean, this titration is such a classic experiment in chemistry. You can't go through a general chemistry class without having significant experience doing titrations and titration calculations. All right. No questions. We'll move on to the next problem. And that is, a work and heat calculation. Try to get all this stuff off. So this will be question number 5 on your practice test. So we did 1 and 2 and 3 and 4, and now we're on question 5. And in question 5, we have this cylinder that has gas in it, and there's a piston that holds the gas in place. And here's our gas sample. And there's a pressure of 2 atmospheres. And that you're going to consider to be the pressure exerted on the gas, or the same as the pressure of the gas. And the initial volume of this gas is 6 liters. 6 liters. Let's say 6.0 liters. And now we're going to compress that gas. We let that 2 atmospheres of pressure push that piston down to compress the gas to a smaller volume. And we get this. Now here's our gas. And we're still going to assume that the pressure pushing down on it is 2 atmospheres. But now the volume, we're going to call this, the final state. This will be the initial state. The initial volume was 6 liters. The final volume is what? 1 liter. And you're told that During this process, this is a compression process. We're compressing the gas into a smaller volume. And you're told that as a result of this, delta E for the process, the total energy change of the gas is equal to, what are you told there? 1,013 joules, positive. So that means the energy of the gas is increased as we compressed it, because remember, delta E is the final energy minus the initial energy. And so the energy of the system is increased by 1,013 joules. But what we want to know is what is Q and W? What is the heat flow and workflow for that process? And remember that the change in the internal energy for any system undergoing any process will always be equal to Q plus W, where Q is the energy change due to heat flow. And remember, heat flow is the transfer of energy through the random collisions of particles, the molecules that make up a system, and work is the organized, synchronized, coordinated, or the energy exchange through organized, synchronized, coordinated motion. But what we want to know is how much of this total energy change was due to heat flow, Q, and how much was equal to, or how much was coming from work. Well, we have an equation for calculating the work. Work is equal to minus the pressure times the change in volume. Know that equation. You will definitely use it in the test on Thursday. And so we just plug and chug here. Well, first let's calculate delta V. What is delta V? That is the final volume where we end up minus the initial volume where we started. Remember that Greek letter delta means change, means final minus initial. And our final volume was 1 liter, and our initial volume was 6 liters. So what we get is minus 5.0 liters. That's our volume change. So now we can calculate the work, because the work, as we see here, is equal to minus the pressure, which is 2 atmospheres, times the magnitude of volume change, which is -5. So we have -2 atmospheres times the volume change, which is -5.0 liters. And we have a negative times a negative, and that is going to give us positive 10 atmosphere liters. Notice those are the units that are left, atmosphere times liter. And that is indeed an energy unit, atmosphere liters, but it's not an energy unit we typically like to use. We usually use either calories or joules. So we're going to take our work of 10 atmosphere liters, and we're going to multiply it by a conversion factor to convert it into joules. And you do not have to memorize this conversion factor. It would be given to you in the problem. And you're told in the problem that there are 101 joules, or no, 103, I think, 101.3. Even I don't remember it. 101.3 joules for every 1 atmosphere liter. So there's our conversion factor for converting from positive 10 atmosphere liters into joules. The atmosphere liters will cancel, and you end up with 1,013 joules. So that's the magnitude of work energy for that process. And notice that it's positive. So that means that 1,013 joules of energy entered the system, and our system is the gas, through this organized motion of that piston pushing down on it. So that gives us W, which is 1,013 joules. What must Q be? How much energy was transferred in or out of that gas in the form of heat? Well, we know that delta E was 1,013 joules, and that has to equal Q plus work, and the work is 1,013 joules. So we just plug in for delta E, 1,013. We plug in for the work, our 1,013. So what must Q be for this process? How much energy was transferred into or out of the gas in the form of heat? And that would be 0. Because 1,013 plus 0 is equal to 0 plus 1,013. So we have Q equal to 0 joules, and the work for the process is equal to 1,013 joules. And that's the answer to question number 5. Any questions, concerns on that guy?
No, I don't think so.
Okay. Well, let's look at question number 6 then. Haven, are you okay with everything there?
Yes.
Okay, let's see, it's still just you two. Oh, no, we have other people in here now. Who's the other one? Is this Chi? Or
Yes. It's
okay. So now we're going to go on to problem number 6. And in problem 6, what do we have? We have this chemical reaction, methane, CH4, plus 2 oxygens, 2 moles of O2 gas. CH4 gas becomes carbon dioxide gas and water in the gas state. Okay. And we're going to have 2 waters in order to be balanced. Okay, that's our chemical reaction. And in this case, what we want to know is what is delta H, the enthalpy change for this reaction. What is it equal to? And why are we interested in that? Why do we want to know the enthalpy change for this chemical reaction? And that's because Q, which is equal to the quantity of heat that can be produced by a chemical reaction, is equal to delta H, the change in the enthalpy of the reaction. So if we can calculate the enthalpy change for the reaction, we know what the heat is, how much heat energy that reaction would absorb or would produce. So how do we do that? And we use this equation. Delta H of any and all reactions is going to be equal to, or is equal to, the summation of the heats of formation of the products minus the summation of the heats of formation of the reactants. And notice this is just a final minus initial kind of calculation. Remember, delta is the change, and the change is always the final state minus the initial state. And in chemical reactions, the final state is the product state, and the initial state where we started is the reactants. So this, we just have to fill out this equation. So delta H of the reaction is, what are our products? And our products are 1 mole of carbon dioxide and 2 moles of water. So for the summation, and this is the Greek letter epsilon, which means add up everything that follows. What follows are the heats of formation of the products. We have 1 mole of carbon dioxide, so we want delta H of formation of CO2 plus 2 moles times the heat of formation of water, H2O, in the gas state. And that will be our sum of the heats of formation of the products. That's our final state. Now, we subtract from that the heats of formation of our reactants. And we have 1 mole of methane, so the heat of formation of methane, CH4, plus we have 2 moles of oxygen. So we can keep the balanced equation. We have to use these coefficients. So we have 2 times the heat of formation of the oxygen, O2. So now what do? If we just knew the heat of formation of carbon dioxide and water and methane and O2, we could just plug those values in and we'd have the answer to our problem. And it turns out we do have those. And we get those from this table. This is the standard heat of formation table. And this is attached to your, you see that? This is attached to your, wow, doesn't seem to be working very well. There we go. To your practice test. And we have the various substances and their associated heats of formation in kilojoules per mole. So you just look up these different substances. And so the heat of the reaction is going to be equal to 1 times the heat of formation of carbon dioxide. And you find that on this table. And it turns out that that is equal to negative 393 kilojoules per mole. So that goes there, plus 2 times the heat of formation of water in the gas state. So that's 2 times, and you look up the heat of formation of water in the gas state, and that's equal to minus 286 kilojoules per mole. And that'll be the sum of the heats of formation of our products, minus the sum of the heats of formation of our reactants. And you're told in the problem that the heat of formation of methane is minus 74.85 kilojoules per mole. So that one goes there, plus 2 times the heat of formation of oxygen. And do you know what the heat of formation of O2 is? Anyone? Dun, 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 dun. You should all know that. And that's because the heat of formation of any of the most stable form of any element will always be 0. And the most stable form of the element of oxygen at room temperature and room pressure is O2. And therefore, the heat of formation of that most stable form will have a value of 0 joules. Okay. So now you just add up everything that we have there. And you have to be careful in doing this because you don't want to drop negative signs, right? Keep your negatives because some of them are going to cancel and become positives. So when you take negative 393 plus 2 times negative 286 and subtract from that negative 74.85, you get a heat of reaction that I did not calculate. I don't have a calculator here. Do you guys have a calculator and can fill that in? Minus 265 plus 74, 75 minus 8. That's going to be negative 890. And that would be letter C in the answers. Any questions on that guy? Okay. Now, question number 7 relates to this problem. This is question number 6, right? Question 7 relates to this. And we're going to need this heat energy calculated from number 6, from question 6. So let's, oh, was there any question on this before I erase it all? Gone. All right. So we're going to go to question number 7. And question 7 uses this answer that we got for question number 6. And so let's, and that's the answer from question number 6. But now we're doing question 7. And question 7 is a stoichiometric problem. It says, and there's 2 parts to this. We're supposed to determine the temperature change that would occur for 10 liters of water that was initially at 20 degrees C if it absorbed all the heat energy from this reaction taking place when 10 grams of methane react with oxygen. So we need to do this in 2 steps. Let's say part A. First thing we want to know is how much heat would be produced when 10 grams of methane react by this reaction. Well, it's a stoichiometric problem. And so here's our balanced equation. We already have that. Next step is to convert whatever we have into moles. And so we have 10 grams of methane, and we need to convert that into moles. And there's 1 mole of methane for every 16 grams. So grams will cancel, and we get 0.625 moles of methane. Now, we don't have to calculate or determine a limiting reagent because you're told that we reacted 10 grams of methane with more than enough oxygen to completely consume it. So we've consumed all the methane, the 6.625 moles. And now what we want to do is to take that 0.625 moles of methane and determine how much heat would be produced when that number of moles of methane is reacted by equation 6 up here. And that's where this comes into play, because this is a balanced equation. This is telling us that 1 mole of methane reacts with 2 moles of oxygen to form CO2 in water and forms negative 890 kilojoules. For every 1 mole of methane that reacts, that's how many moles, or excuse me, how many kilojoules of heat energy that are produced. So we can say if we reacted 0.625 moles, which is what 10 grams would represent, and we multiply that by negative 890 kilojoules per mole of methane, and the moles of methane will cancel, but we only have 0.625, and so when we calculate or multiply through by that, we get negative 550, and we're going to use the absolute value of the heat. Granted, the heat is negative. The negative is telling us that that's a quantity of heat that's given up. We're almost out of time for this session, but we're going to use the absolute value of that. There's 890 kilojoules of heat energy that are produced, that are given out when 1 mole of methane reacts. So we take our 0.625 moles of methane, react it times, or multiply it times 890 kilojoules per mole of methane, and we get 556 kilojoules of heat energy that are produced. Okay? And that 556 kilojoules is equal to is equal to 555, 556,000 joules. Okay? And that is Q. So Q, the amount of heat that is given up is 556,000 joules. So that's part A of this problem. Now part B is saying, now imagine all of that heat energy that's created by combusting 10 grams of the methane, all of that 556,000 joules was absorbed by 10 liters of water that's at 20 degrees C. As that heat energy flows into that 10 liters of water, its temperature is going to go up because as heat flows in, temperature goes up. So we want to know how much does the temperature go up. And this is the equation we're going to use. Q is equal to mass times specific heat capacity times temperature change. And this equation is on the test. And what we're assuming is that the Q is 556,000 joules. That's all the heat energy from that reaction, from combusting that 10 grams being absorbed by the water. The mass of the water, well, we have what, 10 liters of water. So says the problem. Yeah, problem says, 10 liters of water, initially at 20 degrees C, absorbs that. So we're going to assume 10 liters, which would be 10,000 milliliters, which would be 10,000 grams. Okay? So 10,000 grams of water times the specific heat capacity of water, which is 4.18 joules per gram per degree C, times delta T. And now we have one equation right here with one unknown, and our one unknown is delta T. So we solve for delta T, which would be 556,000 joules divided by 10,000 grams and divided by the 4.18 joules per gram per degree C. And the only unit that's left is degrees C, because the grams will cancel and the joules will cancel. And what do we get? We get a temperature change of 13.3 degrees C. So that water, that 10 liters of water, which was initially at, 20 degrees C, the temperature will rise by 13.3 degrees. So if it was at 20 degrees C, it's now going to be at 33.3 degrees C. And that would be the answer to question 7. Okay. Now, any questions on this equation? Q is the magnitude of heat energy that's being absorbed by that 10 liters of water. Why did we put 10,000 grams for the mass? Because we had 10 liters, which is 10,000 milliliters. 1 milliliter of water is 1 gram. So that's 10,000 grams times the specific heat capacity of water. That would be given, you don't have to memorize that, times delta T. And we solve for the delta T. Okay. Any questions, comments, or concerns about that question? No? All right. A little more complicated because it was 2 steps. First step, or part A, we had to determine how much heat energy this reaction produced. And we did that using the result from question number 6. And then we did a stoichiometric problem that we said we combusted 10 grams of methane by this reaction. And then we did our stoichiometric calculations, which are up here. And from that, we determined that 556,000 joules of heat energy were produced when 10 grams of methane reacted by this reaction. and we let all 556,000 of that joules of that heat energy be absorbed by the 10 liters of water. And then we could use this very important equation to determine what the temperature change of that water would be as a result of absorbing that quantity of heat. Right? Okay, so let's see if we can get through another question before we run out of time.
We got less than 3 minutes left.
Less than 2 minutes. Let's see if we have one that's real short, easy to answer.
Maybe the ones at the end.
What's that?
Maybe the ones at the end.
Yeah,
They're
I'm
like
looking at
12 and 13.
number 12. Did you say?
Yeah,
True,
maybe
false?
12 and 13 are shorter. Yeah.
Okay, number 12. A, B, C, D, and E. All right, so A says work. W is path independent. If it's path independent, that would mean it would always have the same value regardless of what pathway we took. Like if we're climbing a mountain, let's say this is where we start and this is where we end. Being path independent would mean that whether we go straight up the mountain like this or go around the mountain, you know, in this indirect pathway like that, that the work would be the same. Let's call this path A and this path B. And we'd say work A is equal to work B. And common experience tells us that that is not true. The path does matter. How much work is required to get from point A to point B depends on the pathway you take to get between A and B. So this is actually false. Work is not path independent. Work is path dependent. The magnitude of work required to accomplish a task depends on the pathway you take. B, delta H is a path independent property of a system. And that is true. Delta H is going to be equal to H final minus H initial, regardless of how you get from point A to point B. Right? The enthalpy change for this change versus that one would be identical. So it means it doesn't, we could say delta HA would be equal to delta HB. The change in the enthalpy going straight up will be exactly equal to the enthalpy change taking this indirect pathway. And that's true. And that's because enthalpy is a state function, a state property. And for any and every state function, the change in a state function, the magnitude of its change will always simply be equal to its magnitude of where it ended up minus its magnitude where it started.